Todo bien
Okay,
aquí.
we are online now. Estamos en línea ya todos.
Listo,
Okay,
Prof.
bien. Buenos días a todos. Esto es la red LAFMAT, Red Latinoamericana en Física de Materia Condensada y Ciencias de los Materiales, conformada por universidades latinoamericanas de Perú, la Universidad Nacional Mayor de San Marcos, de Chile, Universidad San Sebastián en Puerto Montt, Chile, en la Universidad Católica del Norte, en Antofagasta, en Chile, de Brasil, Universidad Federal de Pernambuco, en Recife, Universidad Federal Rural de Río de Janeiro, también en Brasil, Venezuela, la Universidad del Oriente, también el IBIC, Instituto Venezolano de Investigaciones Científicas, la Universidad de Zulia, Colombia, la Universidad Nacional de Colombia, en México, el Sinvestar de México y el Centro de Estudios Avanzados en Materiales en México también. El día de hoy tenemos un invitado muy especial, que es el profesor Montu Saxena. Es muy buen amigo, también en Latinoamérica. El profesor Montu Saxena visitó Perú, la Universidad Nacional Mayor de San Marcos, en Perú, en el 2016, cuando se realizó la primera conferencia latinoamericana de superconductividad y magnetismo. Luego, el año pasado, 2023, se realizó la segunda versión de la conferencia, también en la Universidad Nacional Mayor de San Marcos, pero lamentablemente no pudo atender por motivos de otros compromisos. Sin embargo, se ha comprometido en que la siguiente versión de la conferencia, que se va a realizar en Colombia, va a participar en 2025-2026. Bien, el profesor Montu Saxena es profesor en la Universidad de Cambridge. Él pertenece al laboratorio Cavendish, Departamento de Física de la Universidad de Cambridge. Es un especialista, tiene varias publicaciones en Nature, hace colaboraciones también con universidades alrededor del mundo, es un gran amigo y está dispuesto a poder armar colaboraciones con cualquier universidad de la red y a hacer trabajar en conjunto con estudiantes, investigadores, etc. Well, Professor Montu Saxena, thank you very much to be here, and you can start your talk and share your screen and start your talk now.
Thank you, Luis, for the kind introduction. I will share my screen and project my talk.
We can see your screen now. Yeah.
And the full screen now, hopefully, yeah?
Yeah, now the full screen is okay.
And the slides are changing, yes?
Yeah, it's changing as well.
Okay, good. Okay, very good. Thank you so much. It's a great pleasure and honor to be invited to this wonderful network. And it's really amazing to see, despite the global challenges, you're continuing to connect physicists around the world. And Latin America has a very special place for me. Although I'm from India, I spent my student years in United States. And one summer in my second year, I had the great pleasure, a learning experience to travel all the way by car with some colleagues and some friends from Latin America, all the way through Central America, from via Mexico down all the way to through Colombia, Venezuela, eventually Brazil and Peru. So those were my first experiences. And after that, I've had the great opportunity again to attend the conferences and continue our collaboration with very many colleagues in Latin America. But I think perhaps that needs to be increased a little bit more, and we'll come back to that. And today, I will talk you through not so much of a talk only, but also my research program and why I do what I do and how we think about physics and how I'm an experimentalist. So we'll talk about experimental techniques as well and development of those. So my very broad title today is Emergence and Criticality in Hunt for Novel Quantum Order, and we'll define all of these words as we go across. And if I forget, do remind me in your questions. because one gets carried away with one's own data sometimes. And so as Luis already said, I work at Cavendish Laboratory, University of Cambridge. And of course, yes, one important thing. I think the most difficult thing about me is my name. So he just introduced me as Montu Saxena. This is how most people know me. But if you were going to find me by my publications, you'll have to look for my formal name, which is this Siddharth Saxena. So moving ahead, I want to take you to a concept. And this is something now, when I started in this field, used to be in 1990s, it's something very new and contested, and many people didn't agree with what the different interpretations are, and the contestation continues, but general principles are now understood. So for those who are new to this concept, or even if you are old to the concept, I'll tell you how I think about it myself. So the basic premise here is that once we are through our understanding of classical phase transitions, and if you can see my cursor, hopefully, so this temperature axis is where we think about in terms of classical phase transitions, meaning that phase transitions, for instance, water becoming ice, becoming steam, they come with a change in entropy or order or disorder. And at each stage, we have a certain language, both conceptual and mathematical, with which we can describe these phase transitions. And however, there is another aspect to the story, which is what I hope I can convey to you today, because it's conceptually it's a great way to search for new things, and I'll convey why that so. So if you were to take a system which is already ordered in temperature regime, and we were to apply pressure to it, in other words, if you were to change its lattice density, increase its lattice density uniformly, in some ways we have lowered its entropy or lowered its disorder in some way. And in doing so, the system naturally doesn't feel the need to remain ordered anymore. So the transition temperature goes down a little bit as a function of pressure. And we can keep playing this game and suppress this order completely. Then, if you look at our phase diagram, we have now an ordered state and something else across. So is it disorder, or is it quantum order or novel order? That's the point that we're trying to make. That's the first point. The second thing, perhaps even more interesting, is while trying to build this conceptual idea of a quantum phase transition, meaning that a phase transition which happens at zero temperature, meaning there is no change in entropy when it crosses this boundary, unlike the classical order where there's a change in entropy always when you have a phase transition. So we end up with understanding the point that there's a lot of entropy which is squashed into this corner of the phase diagram, and which makes many states equivalent, and these states are not necessarily quantum, because we're at very low temperatures where we have removed any thermal aspects or minimized them where they're not energetically relevant. And in this regime, many new things can emerge, and one cannot predict that from a standard theoretical or phase transition picture, because this is where we come to the notion of emergence, that you have made the energy states of many things similar or equivalent, and whichever one can win in a very delicate tuning of these things. And the most perhaps prominent, most visible of these states is emergence of superconductivity, which happens in this state. So this is a superconductivity which is somewhat special in terms of how we understand it, and I'll convey to you how that can be understood. But the key thing to remember always is that this superconductivity, or perhaps other things which are happening, only happen in this critical phase transition. They don't happen out here further away, in either direction, only in the vicinity of critical phase transition. Now that's an important point to keep in mind. So to make a kind of a public analogy, or a physics one, that if you're going to, I don't know, to hunt for a tiger or some large whatever cat, you're going to go to a unpopulated area in some sense, or the thing that's populated more by nature, rather than when lots of people live. So lots of people, in our case, is thermal physics, thermal fluctuations, and the nature is the quantum effects, which allow us to which nurture these states, which then we can find if we go into the right place to look for them. So that's just to think about for students amongst us. So this is the starting point, and if we look at, and this kind of these pictures and descriptions are now become very common in many talks. People start with these things, but everyone has something different to say about it. And what I have to say about it is that if you look at this idea of tuning with lattice density or pressure, which can also be replaced by other parameters like doping, or by application of strain or field. But pressure seems to be the cleanest one of them all. But nevertheless, the tuning of lattice density always leads to this creation of phase boundaries, where at the lowest temperature, new phenomena emerges. So qualitatively, you can see across a wide variety of systems, superfluid helium-3, organic materials, the oxide, perovskites, as well as intermetallic systems, you see these things. So these are magnetic examples, where magnetism is tuned in some way and it gives way to something new. And that's one now well-established case study. While more emerging one is that it's not only the magnetic order, but also charge order, i.e. charge density waves, or even dielectric materials where you have ferroelectric order, can potentially show something of this kind. And here's an early example of established material, but we will look at new cases and think about them, right? So that's the premise of what we will do conceptually, i.e. tuning of ordered states to a quantum phase transition or vicinity of quantum phase transition and emergence of new states there, and then try to understand what's new and interesting about these states. So, as I said, I'm an experimentalist, and to do a lot of these experiments, and many of you obviously are aware of these standard methods that are deployed, i.e. dilution fridges, or other forms of cooling systems. Less common is the adiabatic demagnetization refrigerator, and this is something that we have pioneered in many ways. It's a technology or concept which emerged more than 100 years ago, but it could not be functionalized, could not be scaled. And I'm going to spend a little bit of time talking about this because we are talking to a Latin American audience, and you'll see why in a second. Then the third thing is high pressure, which is what I showed you in the phase diagram as a valuable tool to tune together with it. Of course, there is also a magnetic field involved, an electric field involved, and we'll address that as we go along. So let me spend a few minutes on talking about spin-based refrigeration technologies. So again, all the experts know what this is, but just to put it in different words, so think about the same picture we were discussing a second ago, that you have a system which is order at the verge of order. So in this case, a system of spins. And if you apply a magnetic field to such a spin, so you take a system which has lots of free spins and you apply a magnetic field to it, put in a magnet, what happens is that you align all the spins within the system to the field. So it's like going from a liquid to ice, right? It's frozen now. However, frozen analogy only partly works till the next step happens. So when you remove the field, you take it out of the field, your sample, where the spins start to disorder again. So when they disorder, they need energy. So whatever bath they're connected to, they extract the heat from it. So this becomes a solid state cooling. So it doesn't use pumps, it doesn't use liquids. It is effectively a function of making an entropic cycle, adiabatic cycle, to cool using magnetic field. And I would say we have further examples I will get to. It's not only limited to magnetic fields, it's also options here to do using electric field, electrocaloric methods, and also with new multiferroic materials, we can look at magnetoelectric cooling. So this is a very, how to say, a forward-looking way of cooling, because helium is a depleting resource in the world. But it also, if you go back for a second, it's a very complex, and I think we have some colleagues here, Smardo particularly, who have been, how to say, heroes of getting such complex technology working in very difficult experimental conditions in Latin America. But it has remained limited globally. It's not only about Latin America, because it's so complex, it's so expensive, it requires large infrastructure, and it's because it's expensive, people don't let younger students or researchers, easily, work on it. So it limits it makes quantum science, hunt for quantum states, elite endeavor, and those in the hands of few and the rich. But and it's beginning to sound very political here, but if you think about it, it's a practical issue. Practical meaning that we need to find more and more materials which have more quantum functionality, which is what's going to pull us out of energy, security issues, environmental issues, and this is the heart of it. And given that Latin America, particularly, is extremely well endowed with transition and rare earth magnetic materials, it can, I believe that it can, lead the way in at least in this area of cooling. And I don't have my general slide here for a purpose, because we'll do a scientific talk, but I wanted you to think for 1 second that are there more refrigerators in the world? Or refrigerators meaning what you cool your food with, but also your air conditioners, your supermarkets, your refrigerated trucks, your planes, container ships, cooling vaccines, food, everything else. Cooling is done by some form of refrigeration. And just imagine, are there more refrigerators in the world, or there are more cars? So much discussion is about making electrical vehicles as the key thing we should do, which is very important, and I totally agree that we should do for other modes of using energy, but we need to solve refrigeration. And I think what we have proven in the lab can be very useful for both as a technology itself, but also, of course, it makes experiments better to search for materials. So it's a thing I would like you to think about, and we can maybe discuss it in Q&A later. So I'm going to move away from all that industrial and political philosophy and back to our science. And so why we were using this refrigerator is to be able to create phase diagrams, meaning that we can easily and quickly create a pressure temperature phase diagram in which we have a precise measurement of properties like resistivity, magnetism, and other thermodynamic properties, but also conduct experiments with neutron scattering and other things. So the conceptual notion I bring back is the one that we've already discussed. And here is an example, a very old now example, published back in 1998 of superconductivity in cerium palladium to silicon 2, which is a material which is an intermetallic antiferromagnet, which orders a 10 Kelvin. Then with application of what today we'll say very simple pressures, but back then relatively high pressures, superconductivity is found exactly where magnetism was suppressed. And there are two things to take away from here. So one which will be very important in our analysis of other newer things we're doing now. The first thing to take away from here is the fact that superconductivity only appears here, just near the phase transition. It doesn't happen here or further away. Here's real data we're showing you, not just the cartoon, which we're showing you here. But the other important thing, which is equally important, as important as superconductivity, is the state above superconductivity, the normal state. And the normal state here you can see is if you are a specialist, you'll notice immediately that the power law 5/4 represents a deviation from Fermi liquid picture, which should be T squared. So again, for the newcomers, what does that mean? It means that in a normal metal, when you go down to lowest temperatures, you find that once all the thermal fluctuations have become very low in energy or not present, defects, the material is clean enough, there are no defects. Only thing that you have left is the scattering from electrons with each other. And that's a quadratic, that manifests itself in quadratic behavior in temperatures of T squared. And that's the standard model of condensed matter physics, which is the Fermi liquid theory. And then we have now, at least since 1998, if not before, because these ideas were explored before even, something what we call non-Fermi liquid state, where you break this canonical state, because you create fluctuations, magnetic fluctuations in this case. When you're suppressing magnetism down towards zero, it starts to fluctuate. So you have a system in which, in your mind, you can build a picture. The picture being that the electrons are scattering from these magnetic fluctuations, and that's what gives you these different power laws that come up. So scattering. So since there's not just electrons left and it's not thermal, something else is there, which is this quantum fluctuation of, or you can call it a manganon rather than a phonon, and your electrons in here scattered from it, and that also in a sense creates an attractive potential. So it's like because once your electrons scatters off this fluctuation, they both lose energy, and the physics become that of dissipative modes in the system. Yeah, this is an important consideration. So dissipation, basically, the fluctuation dies down immediately, and an electron loses energy. If you want to think in a pseudo classical way, is that you have thrown a pebble into honey, and it deforms, but it cannot propagate out. Since it cannot propagate out, it starts to retract. When it retracts, if there's something, they're low energy enough, it'll trap it, and that creates a condensate or Cooper pair type of thing, which is here in this case created by magnetism. So the final point here is that you have superconductivity, which is created by magnetic fluctuations, i.e. magnetism, not destroyed by magnetism in a simple way as does it is normal superconductivity. And you have a state which is now not anymore the canonical Fermi liquid state. I want you to keep, I'm spending some time because these things will appear later and help us understand the phenomena that we are measuring these days. And for the students out there, both theorists and experimentalists, so just look at what we call it. We call it that state because it's not anymore Fermi liquid. We call it non-Fermi liquid state. And that's quite a funny, slightly shameful thing. We don't have any idea what it is. We call it non-Fermi. We call it what it is not rather than what it is. So if you're able to sort this out, it could carry your name like the Fermi liquid before it. So it's a motivation to think about, study these phenomena. And that's what I try to tell if you are the type who wants your name with a phenomena name, here is a sitting problem for you. Solve it and it'll be there. I have so far failed, but I try to find more and more cases to see if we can understand it. So having established that fundamental thing, I want to also say, don't get trapped by the fact that there can only be superconductivity that is interesting, and that only thing you need is an antiferromagnet. No, the answer is that if you actually bring in other things like ferromagnets, you get even more fantastic stuff happening. So for one now, is the more established. For instance, you can get skyrmions. That's not superconductivity, but it's another form of novel quantum order that emerges. And now even famous persons like Albert Fert and those who have Nobel Prize in magnetism areas, they're trying to exploit this for device making and for practical application, which is quite satisfying to see. And similarly, superconductivity itself in a ferromagnet changes its form, and it can be triplet superconductivity, which is thing again we can discuss more. But it's a different, and we have very few examples of this. But one striking one is this particular one, superconductivity in iron, pure iron. So if you look at this phase diagram, I'd like to show this very quickly, that if you, so this pressure, 20 GPa, 200 kilobar, and about, this is around the pressure of the Earth's core. So historically, the geologists have always called this area of the phase diagram as non-magnetic. So of course, they're at high temperatures. They're here somewhere, but the magnetism to them is a standard long-range order. But for physicists, it should be clear that magnetism comes in all variety of time, space and time continuities, and a lot of the short-range order is considered in terms of magnetic susceptibility. So you'll find that the magnetic susceptibility of iron, where it's supposed to be non-magnetic, is about higher than palladium. What is also surprising is that actually, if you cool the system down, at about around 2 Kelvin, it goes superconducting. And so this is very interesting from our condensed matter solid state physics point of view. But on the other hand, it's also interesting that magnetism and some form persists in Earth's core, and that has relevance towards understanding geodynamo of the Earth and its relevance to how the weather patterns change and generally the physics of the Earth. So this, our very niche area, can also have a bigger impact in understanding other properties. But look at the resistivity of iron, and you will see that how before superconductivity we again see deviation from the T-square behavior. So magnetic fluctuations are definitely there. They can be measured through, of course, neutron scattering and other methods and so on. But even having established that method of analyzing resistivity, we can understand how these new quantum states are emerging, both in form of superconductivity, but also in the normal state beforehand. So we still have relatively few examples of ferromagnetic superconductors, and vast majority of them are uranium materials, similar to my original work on uranium germanium 2. And one debates, of course, and rightly debates very specific details which are different between these materials, but generally speaking, as a universality class kind of a thing, they are still very similar. But debate is still on. We need to find more answers. Of course, as I showed you, iron is slightly presents. It's a D metal in a simpler case, but comes with its own structural transitions and complexities. But it's quite exciting. There have been analogies made with pnictides and chalcogenides, which have iron-containing materials, which show superconductivity as well. But one could not directly establish the connection always between the magnetic phases, ferromagnetic phases, I mean. And most recently, a massive amount of activity in last 5 or 6 years have been on the newly discovered uranium tellurium 2. Emphasis there is much more on the superconductivity and its coexistence with magnetic fields. And I have not got into that. This is an area that I'm very much interested in as an observer rather than as a participant. And maybe I will get into it when I see I can contribute to it. But it's a direct kind of a continuity conceptually in looking for these materials. This superconductivity or quantum states in these kind of materials. Now I want to jump into a slightly different part of the story, that if you look at in the early days of finding superconducting antiferromagnetic compounds, one also finds that if you can create you can actually enhance superconductivity if you make the system more 2D. And this, of course, is very obvious in case of high TC materials, but as observable, because they are very 2D and they have very high TC. On the other hand, to prove that point, one had to come up with a simpler example. And this was the case, where you could see you went from a 3D 3 by inserting a layer of rhodium in the middle and made it more 2D. So conceptually, what's happening? So I gave you the picture of that throwing pebble in the honey analogy, that you throw the pebble, distorts, retracts, it captures. But imagine that in a 3D system, your system is wobbling in different directions. So in some sense, it makes it energetically difficult for the pairs to form, and things have to be more, interaction have to be stronger and often at lower temperatures, where these things get calmer for the pairing to happen. But if you constrain it to 2D, your motion is not everywhere, not in 3 dimensions, but only in 2, and increases the chance of pairing. This is a one interpretation, and there are different ways of thinking about it. But it allows us as experimentalists to not always having to solve the equation to understand something. We can think about why do we need 2D, and how in terms of materials, how in terms of talking to our chemistry, material science colleagues, we can think of different materials that they can make for us, or we can make with them, to hunt for this phenomena. That's our message today, is hunting for this phenomena by playing with parameters. So, and I'll not spend too much time on it. Our initial discovery away from intermetallics was using this philosophy, was to using graphite. And this was something that happened before graphene became so popular, was to find superconductivity in C6 calcium and C6 ytterbium. And these are not, in fact, magnetic compounds at all. It's a different kind of physics which gives superconductivity here. But nevertheless, in a 2D material with the right intercalation, you can actually increase the TC as well. So dimensionality has an important role in the story. But graphite or graphene or carbon compounds have their own complexity. Particularly as an experimentalist, they come with a high degree of air sensitivity and very specialized sample handling. So number of experiments one can do become very, again, niche, and again, then they belong in particular kind of labs. So we thought, okay, what can we? So we have intermetallics where we can see this, and we have a handle through pressure and so on. We have graphite here. We can see things where we can maybe use intercalation as a tool, and we see emergence of this superconductivity. About sort of roughly 10 years ago, we decided to pursue our luck with this newer family of materials. And some of you, if you attended the Peru meeting, the Latin meeting in November, you would have seen some of these results. And these results are related to this family of materials known as TMPX3, where you can have 2D layers. So here there is, we are starting not with a metal, so starting with an insulator, which is magnetic. And there are a number of different metal species one can insert. So you have a transition metal, TM, then we have phosphorus, and then X can be, in our case, sulfur or selenium. So this is a family materials which are most often not insulators, sometimes charged insulators, but almost never band insulators. But also see that the arrangement is hexagonal in that sense. So a bit like graphene. Yeah. So this time we had to deploy diamond anvil cells rather than the clamp cells, the 30 kilobar ones, to study these materials. And those who are again unfamiliar with the story, so we have basically 400 micron space in which we put a small sample. We fill this space with a liquid or a gas, a liquid gas, and then close it with the diamonds from both sides and to create hydrostatic pressure, and then we can put this on a cryostat to make the measurements. So we started with a insulating material where basically resistivity is difficult to measure, but we followed it, and in a sense, I'm telling you a story a little bit backwards. We needed to understand what the structure is doing. And if you look at the structure in this material, which, by the way, probably I'll come to it again, is been named recently in the last few years as magnetic graphene, because you can peel these things down to a single layer. And also, they are unlike graphite or other chalcogenide materials. They're not air sensitive at all. You can actually do them quite easily. So when you apply pressure to not the single layer, I mean then the bulk single crystal or powder, what you see is that with the application of small pressure, the layers slide, and then at highest pressure they resettle and rebond. So effectively, you take a 2D material and you apply pressure to it, and you start to see it becoming more 3D at highest pressures, which is kind of interesting in its own right. This work was published in 2018, the structural part. And if you want to follow that, looking at the D-spacing, this is what you see. So FePS3 was showing you the red one. And what you find is that I'll show you this data in a second, that at the moment where this collapse or van der Waals collapse happens, system goes from 2D to 3D, it also metallizes. And I will study mainly the case of iron PS3 for you in this talk, but its neighboring species, friends or brothers, also manganese PS3 and nickel PS3 also show this kind of behavior. And these are very interesting materials for a number of different reasons. Here's a review of that you can read. But getting down to the details. So FePS3 here we have at starting pressures before the van der Waals collapse, you see that it's still pretty high resistivity. And then you cross over about around 100 kilobar from an insulator or bad metal to metallic state, and system becomes quite metallic. Two things to point out, there are many things here, but two to highlight. One thing is that the power law comes back to life again. So it's a magnetic insulator which becomes a magnetic metal, and magnetic metal with no long range order. So previously it had short range order. Sorry, it had long range order, long range antiferromagnetism, which under pressure gives way to becoming a magnetic metal with short range fluctuation order, which shows up in resistivity. And unlike intermetallics or other things, here it persists to pretty high temperatures compared to those materials. And also we find that there's some other interesting behavior at low temperatures. At the very low temperature, we have an upturn. So, which we're trying to understand. This could potentially be something like a Kondo effect, which is being nucleated because of magnetic localization that might be happening in these materials. But this is completely, we have no proof of that. It's just a speculation. But then the metal to insulator transition or Mott transition in the material is quite interesting, and the fact that it comes with this new correlated behavior or breakdown of Fermi liquid state is also interesting. We studied the magnetism using probably the first high pressure neutron experiments to these kind of pressures, where we could actually follow the wave vector and look at the broad short range features which appears in this HP2 range, and mixes into this new kind of a magnetic metal. More details to be discussed here. This was very much liked by the ILL, where we did this experiment for the first time. So we developed together with from a lab-based high pressure to neutron-based high pressure. working with some people who have done this work in the past, who have developed this technique, like Stefan Klotz and colleagues. But they had never gone to the lower temperatures or look at materials which had no long-range order. In fact, transition from a full long-range order to a fluctuating order state it was quite a difficult experiment, but we were able to do it, and that produced this phase diagram. So if you were to lay out the magnetic and structural phase diagram, you get this picture, which is you see antiferromantism giving way to those structural transitions I mentioned. Eventually, it metallizes, and then you get short-range magnetic order. So this is, you can see insulator. It's a structural mix to again a new kind of insulator, and eventually crash into a magnetic metal. So this result was slightly controversial because previous people using XMCD work had presented the idea that the system is not magnetic. And I think this is why I was showing you the iron results before, that often people, when they look for just long-range order, and then when they don't find it, they often tend to classify something as non-magnetic. But in terms of short-range order and magnetic fluctuations, those of us who are more interested in quantum state often look for it specifically, and if you and some cases we find it as in here. A small segue so we haven't found superconductivity so far in FEPS3, but FEPSE3, it's So FEPSE3, the selenium version of the compound, actually shows superconductivity according to the other authors. And this is something we are now considering as to why and why not. And if I ever give a next talk, I will show you the results, our results on FEPSE3. So I won't say very much, but they differ quite widely from this work published earlier. But let's keeping to what we have published. FEPS3 is, as I said, we're following up this work on from FEPS3, where we see the C-axis collapse, which completes around 14 GPa to nickel PS3 and manganese PS3. These materials, and we find this new kind of a magnetic order, new magnetic metal emerging at high pressures. Now the job is to see what kind of quantum states we can characterize in these areas. And we're using all the tools, both resistivity, magnetization. Unfortunately, at such high pressures, we cannot do heat capacity, which will be very useful, but it's a thing to develop. And again, if people have ideas about that, we'd be very happy to discuss collaborations. Just a short, literally a 20-second thing to say that since this kind of material can be peeled down to a single layer, and it can, and it's not air sensitive, it is of interest to those who are interested in making devices. And some of our collaborators working with us did initial testing to see that how devices can be made, and it's a very promising material in a sense that the world needs something other than silicon and maybe germanium, which has more tunable band gaps with strain or other reasons, and has further functionality of magnetism with it as solutions to our future electronics and other things. And this could be a possible player. Of course, I'm not an engineer and I can't say too much about it, but our chemists and engineering friends have shown interest in it, especially since it's tunable, it's magnetic, it's 2D, which can go down to 1D or 3D, and it's not air sensitive. So it gives a lot of handle to try. I'm looking at time. I think, yeah, we have a few more minutes to just kind of run through another aspect of the problem, which I promised. So I've shown you how going, one aspect was how we changed dimensionality, and other format was how we could move away from magnetism to dielectric or charge ordered behavior. And in this regard, another part of the work we have focused on is to look at something that's been known classically for many years, which is the ferroelectric systems. So in aspect of quantum criticalities, in aspect of searching for new quantum states. So ferroelectrics are an avenue in this area. Why? So first of all, we can make, of course, analogies to what we understand. And now the picture being that if you look at the systems which are whether magnetic or charge ordered, but are metallic, have this fantastic tendency when you tune them down to zero, they spit out this brilliant new phenomena: superconductivities, fermions, non-Fermi liquid state, all kinds of things. And we get quite, I mean, they're amazing. But as a purist in physics, we forgot what we actually started the reason why the study for. We wanted to understand quantum phase transitions, which get either disrupted or masked by this more exotic phenomena that comes in front of us. And the ferroelectrics offer a fantastic new model material where we can tune the charged state down to zero. However, there are no electrons in the picture. So a number of new fundamentally interesting things happen, which I will share with you very, very quickly. But conceptually, you imagine we take the picture of this throwing pebble in the honey away, and we bring a different picture in. The picture of throwing the natural thing, throwing a pebble in a pond, in water. So you throw pebble in the water and the wave propagates. So here, when we create this quantum fluctuation out of a dielectric material, it has that property. So we create a quantum fluctuation which cannot be damped by electrons in the system, only by long-range interaction and forces. And how do we think about this physics is new and exciting area in many ways. It's kind of bringing back what in the past people have done with ferroelectrics, but thinking about its quantum aspects. For this, we selected initially two known materials because we were new to this field. We were not the people who understand dielectrics that much, at least I didn't. So we went for the materials which are very well known. So we can start with something that's known. Strontium titanate is probably one of the most studied material in science. Often people call it Drosophila, like the fruit fly of the condensed matter physics, where you can people keep studying it forever. And it's a cubic perovskite, but interestingly, it's something that we already understand lies near a quantum critical point, because if you perturb it anyway, you do anything to it, you shine light on it, you squeeze it, you dope it, it immediately tends to become ferroelectric. So that means that it has been tuned out naturally. It's sitting around that cusp. So to think about it, and then, sorry, let me also say that, you can also put isotope instead of oxygen 816, which is a normal strontium titanate, you put oxygen 18, it orders again. And that's oxygen, that's your strontium titanate, oxygen 18, which shows you order around 30 Kelvin. But if you look at the literature on this, you can go back to Buller and Burkhardt in 1979, even further, 73. This has been theoretically considered many times, but there were very few experiments at low temperatures, definitely at low temperature, high pressures, which can actually test some of these things. So conceptually, what we're looking at is this. So what we have, if we can just quickly recap this honey versus water analogy I gave you. So you are looking at dissipative modes, right? It's a relaxation rate, which is important, which gives you then your properties, and in a magnetic system, right? But if you go to a ferroelectric system, you are looking at the dispersion, right? So here you have dissipative modes, here you have propagative modes, quantum propagative modes. And what physics they can give you is something we're going to try to see what has come out of experiments so far. So just using the previous picture, we can solve for free energy, and we can look for the measurable properties, say susceptibility, thermal conductivity, heat capacity, and thermal expansion. We will focus almost entirely on susceptibility measurements initially, but it also gives you a sense of what the phase diagram. So we're sitting here in the phase diagram. For strontium titanate, this is where it sits naturally. And if you look through experiments, and we had to actually build low temperature dielectric measurements. It took a long time, but we were successful. You can actually measure the epsilon, the dielectric constant, and you find that it actually fits a t-square, which is the quantum critical power law in the story, which is given here, and sorry, these things are just moving on their own. So then you can see down. What is interesting is that at very low temperatures, we found that if you have a very precise measurement, just look at these numbers, 5.07, 5.04, that level of sensitivity, if you can achieve that, so experimental development is critical to finding this very subtle low temperature form of phenomena. You find some effect, and I'll go into this effect in a minute. You find, in fact, in strontium titanate, if you model it using previous theory, it also qualitatively gives you a similar effect. This was, in fact, originally already discussed by those 73, 79 papers that we're talking about, but they were never able to fully measure it and tune it. And this is where our contribution comes in. And so if you look at the phenomena here and how we can explain it, so you have magnetic susceptibility, which of course is being reformulated because you're suppressing the long range order. Here it's been done naturally. And then you have the acoustic phonon near quantum critical point, which possibly coupled to it to give it a local minima. This is based on the Kamilitsky paper from 71, in fact, and it was an earlier one even. But also it was done in our collaboration with us in 2008 when theoretically we looked at, but we also found something similar in potassium tantalate. So it's not some artifact of the material or even of the cryostat. Now of course, it's been measured quite comprehensively. But let's go back to strontium titanate for a second and study it. So conceptually, normal strontium titanate, oxygen 16.1, sits at the quantum critical point. Naturally, the one that you can buy or you can grow. If you make oxygen 18.1, it's ordered at 30 Kelvin, as I showed you. But if you look at the properties, for instance, if you were to make it push it by using other control parameter, let's say pressure, you find that it looks more like potassium tantalate at high pressures, away from quantum critical, further away from quantum critical point. So for this, we had to develop machinery. So we were among the first to be able to take the coax inside the pressure cell. Those I'm not going to spend time on it now because we're short of time. Into the high pressure space, and also couple this to millikelvin adiabatic Demag refrigerators to present the data to you. So with a very small pressure, you can see you can collapse this very high, what is known as the quantum paraelectric susceptibility. Strontium titanate does not order, as I mentioned, by itself, but if you apply pressure, you push it away from quantum critical point. And what is even more exciting is that if you take the power law, you can see how it persists over a long, up to about nearly 40 Kelvin in a quantum critical state. And those who make devices and other things, and bolometers, should be aware of this. This thing is lurking underneath the surface and causing new couplings. But if you look at potassium tantalate, you find that it doesn't order because it's further away from this thing. But if you take strontium titanate and you plot the same thing here, but you apply pressure and you push strontium titanate to look more like potassium tantalate. See, it looks like that. So here, as we had this picture before, so you by using pressure, you push this to here. So this is done here with the same data on the same input. It's all on one material, which starts to look like that. So this quantum tunability of this tunability of quantum states in these materials is a phenomena which we are quite happy to establish. But there are some other aspects in the final thing that I want to end today by. So this is just to show you that if you're at ambient pressure, this is your quantum regime. You can tune it. So normally one thinks that when we tune it, we increase the quantum space, but depending on the material, you can actually reduce the quantum space, make it more classical, but that doesn't make it less interesting. Why? So if you look at this low temp 2K state that I showed you, and we show that how it grows with pressure. So in pressure, with pressure, this new state actually grows, and if you renormalize it, it collapses back to the quantum critical point. So here's a classical state, a system which is becoming classical, but by correlation, it can be related to the quantum critical point. So here I'm trying to push my agenda of saying the hunt for quantum critical point. It still can give you new insights and new discoveries. But it's not only that. So here is a new phase diagram of strontium titanate. Here we can see quantum paraelectric behavior, which is traditionally known, which starts to grow. And then we have a very low temperature below that 2K state, a new state, which is called quantum polar acoustic state, which is a kind of a phenomena where you can invoke understanding from order by disorder. So you have lots of things which are fluctuating, but certain couplings can create a coherent quantum state. So what does it mean? We have to understand that I cannot say that we understand this. This is published in PNAS in 2020 during the pandemic. But there are certain conjectures we can make. The first one is this one, where you can see how this state is growing. The second one is that the susceptibility scales with quantum critical point. And the final point about this is that if you look at the susceptibility, you don't find, if you continue with the free energy calculation that I showed you earlier, the theory gives you that it should be a quadratic dependence at high temperatures or at higher pressures, which we don't find. However, some of the theorist friends have suggested that what we have are microdomains, and they have calculated this, and we have also checked the calculation. You find the coupling with this. So this is the insulating version of a non-Fermi electronic state. Yeah. So strontium titanate is an insulator. You have while there are no electrons present, you can still see a wide variety of tunability is happening, and new states are emerging at very low temperatures. So we don't often think about this vibrant quantum phenomena or quantum states emerging in insulators, which can also be tuned. And that has an interesting consequence beyond what we're thinking, because strontium titanate itself is a superconductor when you put a little bit of electrons in it. So it has a very low density of electrons, which can give superconductivity, and it's been speculated why that can happen. And our picture is that it is some combination of quantum fluctuations and the classical pairing mechanisms can give you superconductivity in this material. We cannot say the superconductivity itself is of exotic type, but the mechanism which creates superconductivity is pretty exotic, which is related to quantum criticality and other phenomena that emerges in this space, this quantum polar acoustic states. We now again have a task in front of us to either prove or disprove this phenomena. So this is a very early stage in that sense, and I wanted to share this kind of a larger meeting because there's a potential to develop collaborative projects here, which go across from back to the superconductivity. And our own results show you that there is certainly, so this is a picture, slightly careful to read. So we have pressure here, temperature here, for the superconductivity and temperature here for the what would have been the ordered dielectric state in strontium titanate. Meaning, if you go to this material, it's a slice that we're showing you of this phase diagram, so it's not a 2D phase diagram. Yeah. I'm showing this also because a lot of this work has involved South American scientists, predominantly from Brazil, but not only, because the Brazilian lab has people from all other parts of Latin America. But nevertheless, this is the beginning of the story. And the thing that I had hinted at the very beginning, that the understanding dielectric state, superconductivity, quantum phenomena is absolutely fascinating in one side, but it also leads us to think about how we can use these even dielectric phase conditions as similar to magnetic ones as cooling engines. So can we, and they are much easier in that sense because we don't need a magnetic field. And they can be made more easily into devices. So can we replace a fan using a system like this? Because they can be miniaturized, they can be more easily, let's say, than many magnetic materials integrated into electronics. And just imagine you have your phone or your laptop or your other things, which is a circuit in which you have an integrated electrocaloric cooling mechanism. And that can help you to both make the computation more efficient, but also use less energy. And then potentially we can harness or push up in temperature some of those more robust quantum effects, and they can serve as multifunctional ones. Please don't ask me what they are. This is just a speculation and excitement from our experimentalists who having seen these states and that we can manipulate them. And so to end, I would say that border of order is a quantum Wild West, which is of course, those who are old enough will know that I'm stealing from an American Taco Bell advertisement that used to happen in a commercial, the border of order. And here we have the similar things happening for us at quantum level. And I will finally show you that all of this is possible because we continue to develop new techniques, not just look for new phenomena. So new materials, new techniques together is essential for us to discover the phenomena, to better resolution in measurement, and make cooling and pressure simpler. And that's where all our tasks lie at the moment. So there are ways of making those, the very ugly picture I showed you how we work with hands under a microscope to do these things. We know how to find ways to automate them. We have certain ideas and projects running. And similar things go with integrating cooling at that well. We're working with countries already, which are in a sense counterpart, and Luis will tell you in Kazakhstan and Uzbekistan, which have lots of mineral wealth, but are using often only as raw materials, but they can be turned into both research possibilities, but also changing the paradigm in terms of energy security and so on. So I won't even bother with summary. I'll flash the number of people who did all this work with me over the years. And there are some of the publications which can give you references to this, but I can send them later. So with that, I will finish the formal part of the talk. I say I very much looking forward to meeting many of you in person, perhaps in Colombia. And the one final thing I would like to say, that I'm having said all the things about Latin America and my love for it and my connection to it, but there's one thing which is left. I have personally never ever supervised a PhD student or master students from Latin America, and I would like to change that. And that I'll leave that open with that, and I'll stop now. Thank you for your attention.
Thank you very much, Professor Montu Saxena, for your very nice talk. Well, now it is time to start with a question from the panelists. First, we are going to start with a question from Venezuela, from the IVIC, Instituto Venezolano de Investigaciones Científicas in Caracas, Venezuela, with Professor Ismarro Bonalde. Ismarro, your camera, please.
Thanks, Luis. Thanks, Montu, for your neat and nice talk. in these subjects, which is quite interesting, and I am part of it. And before I was stopped here in Venezuela, running my lab for about 6 years, but before that, I was working, as you may remember, I was working in this quantum critical points and these quantum states. Did you say something about the FEPS3 and FEPSE3 systems? There, the phase diagram is not quite similar. It's not quite close, I would say, not similar, but quite close to the standard ones in heavy fermions and so on. For example, in FEPES3, which is a superconductor, the other one is not. I didn't see in the phase diagram a quantum critical point. I don't see quite well what is on the left side of the exactly here, just exactly that slide you are showing. What is in the left part of the phase diagram there and in the diagram? I don't see any quantum critical point there.
Sure. So that's a very important point. So there are two, possibly three things to say. First of all, when you think about a heavy fermion phase diagram, you're starting in a metallic state, as opposed to an insulating state. So these are all of these materials starting as insulators. They are magnetic insulators, and the notion of quantum phase transition versus quantum critical point, they are related but separate ideas, right? So you can have a quantum phase space in which your system is, so to be very specific, as you are pushing your magnetism down by whatever method, you are approaching a quantum critical point, but you may miss it if you have a first order transition. But if you have energetically reached low enough temperatures, you have quantum critical fluctuations, which emerge well before the critical point is achieved. And those fluctuations can give you new physics. And that is the conceptual side of things. Experimentally, in these materials, the key challenge is that we're starting with an insulator, which of course is becoming going through structural transitions, and we're using diamond anvil cell, which doesn't have the same level of tunability, let's say a clamp cell would do. So to tune into the narrow phase spaces where the critical point can emerge or could be studied is still something to be done. What we're seeing is that we're going across phase transitions, but we're seeing similar physical manifestation. We're seeing that when system becomes metallic, it shows power laws, or becomes superconducting, right? So it's invoking the quantum phase transition physics more than the quantum critical point. Quantum critical point may be avoided or hidden in there, so you may be seeing, critical endpoints as opposed to a single critical point here, yeah. So that's the bigger part of the answer. The important but smaller part of the answer is that we are looking at 2D materials where you will see extended. So if we even go to the metallic one, let me just go back to that one to make the point. If we go to here, so you can see how very clearly in the 3D one, you have a very neat phase transition and a very nice husk. And here you go with this 2D, you start to see very broad spaces without any clear distinctions, but you're still in a metal, so you can still see it more clearly. If you extrapolate that blue space back to my PS3, PSE3, then you will start to see similarities, at least broadly speaking. Yeah. So let me find that again. Yeah. Sure. Go ahead, please. Yeah.
Yeah. No, and the other point, I understand what you're saying. The other point is that what about the superconductivity here in this material? They are not proved to be unconventional, right?
No. First of all, we don't know because but it's important point to make is that when we say unconventional superconductivity, and this is what I was trying to talk about in a different case of electric, this word has become complicated. So it's semantics. So when we say unconventional, do we mean unconventional mechanism or unconventional pairing symmetry?
No,
Or both?
unconventional pairing symmetry, yes.
Yeah, I know. That's where you come from.
Yeah.
I know that. That's
Yeah.
yeah. So I'm very aware of that. So
okay.
So we're here using it a bit more loosely to say a pairing mechanism can also be unconventional, but it can give you very conventional superconductivity. Of course, we don't know of any case where you have a very conventional pairing mechanism gives you unconventional superconductivity.
Yeah.
So this is a new, in a sense, a new class, potentially. But we don't know. We haven't been able to any kind of measurement that you have done onto this to look at the symmetry. Yes,
yeah. So the other point is that, well, this ferroelectricity and quantum phase states and all this stuff, there has not been much push on that, right?
Well, it's much less attractive because it's for those who are interested in applications and whatever else. It's a very much niche area for dedicated quantum scientists. However, I would say that if you of course, it's only, I mean, both of us know it's not a real measure of it, but if you pick up, for instance, our main paper that we published in 2014 describing the phenomena, this one. So this has more than 200 citations. So that's a measure to say that there is the activity may be less, but interest is there in terms of understanding physics from that. And we have been consistently be able to publish this kind of work in PRL or PNAS or Nature type of material. Again, I don't want to claim that makes it any more superior to anything else. But it just shows level of interest is not low.
Exactly.
Yeah.
Well, I will be if once I have my lab running, I would be quite interested in collaborating with you on this stuff. I think it's very nice, it's very interesting, and in terms of physics, in fact, and it's a lot of new things are there. It's clearly, as you show in your talk.
Yeah, we are very early stages in all of these things. That's why I try to show you not, that's why I had so much of the introduction, so I can claim what we're doing is interesting because we don't have evidence yet.
Well, it is not, but it is not. But if you look at the picture of in the magnetism type of things, the analog one, and we can see that there are a lot of things there that we have to test, to
clean up, to clean up,
exactly. And I will be very happy. I have a high pressure and low temperature facility in my lab, and once we get here in Venezuela a little bit calmed down, I can for sure. It will be interesting in this type of stuff for sure.
We're ready, as you know.
Yeah. I know. Thanks for your talk and your answers, Montu.
Sure. Thank you.
Thank you very much, Professor Ismar Ramonalde from Venezuela. Now we are going to move to Chile with University Católica of Norte from Antofagasta in Chile with Sergio Conejeros. Sergio.
Okay, hello from Chile. Many thanks, Professor Saxena, for your excellent talk. I really enjoyed your presentation. I'm not an expert in this field, but I have some general questions. The first one is related to something that you said about, particularly about this compound, the iron phosphide sulfide. So you said that when materials are reduced from 3D to 2D structure, so then the superconductivity is favors something like that. I think.
So yeah. No, you're right. So I both the two things I said there, and this is partly related to what Ismaldo just asked. Let me show you what I mean. So first of all, here's a phase diagram. Let me just make it bigger so we can see it clearly. So basically at this boundary, right here, yeah, is where it goes from more 2D to more 3D, right?
Okay.
And we have actually a DFT paper out, which basically show you how the electronic structure changes, becomes metallic. What we find is with a similar story, sorry, and there are two things happen. So it also goes from being a long-range magnetically ordered material to a short-range or ordered one as well. The two things happen. So metallicity and change of type of magnetic order. And which is where I was trying to make the analogy with the metallic ones before, that those usually at this stage become superconducting. But so far, we haven't found superconductivity in this one, but we believe it favors it because of our previous, conjecture. And we think it might be at lower temperatures. We just haven't had, same thing, pandemic new, to test it at lower temperatures. But what makes us more hungry for it is that if you go for the selenium one, which is almost the same in every other sense, it's a magnetic insulator, blah, 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 blah. And it also crashes into being a magnetic metal. This one does go superconducting. So we have two questions. One is that if this goes superconducting and doesn't go, why? What's so different about it? So why does selenium one does? Why does sulfur one doesn't? Since you asked, I'm going to muddy the waters a little bit. So we have measured the selenium one also ourselves, and we don't find superconductivity in it. And we haven't published this yet because we don't want to publish incorrectly. But what we think is that it's potentially, and I have to be very apologetic and eat my own hand if I'm wrong, that it possibly is not intrinsic superconductor. This goes back to what Ismail was asking. It's possibly selenium superconductivity, which is showing here rather than this compound itself, because selenium goes superconducting around this kind of type of pressures and these temperatures. So to answer your question after that is that it's possible that there is no superconductivity in these materials at all at these pressures. Yeah. So just to be honest, we absolutely, I'm an experimentalist. I don't have any evidence. This is my evidence I'm putting to you. Yeah.
Okay. So regarding to the same graph, so because I have when you achieve metallization, what happened with the magnetic moment of the iron? In particular, because if you have iron +2, you can have the two state. You can have highest spin state or lowest spin state. So probably you measure that, but
so if you look at
because you in the panel of the left on the previous one. So on the previous slide, so you put something that is not that you didn't you were able to observe some magnetic moment on iron sites at metallization, right? Or
yeah. So two things again. So this is, if you look at the iron itself, this is a phase diagram. So under high pressure, iron itself loses long range order and becomes a highly susceptible material with short range order. Then it's a question of the time scale of the you're measuring at, right? So then if you go back to that plot, this one, so what more or less is what we find here as well. That the system goes from being, so in this case is actually antiferromagnet because we're looking at the full FePS3, but and this is a measurement using neutrons. So we can directly not see any long range order at all, but we definitely see we can derive using reverse Monte Carlo from this data. This is what you get. So if you have a look at this PRX paper, you will see how we treated the data, but so there's no how to say long range order, but there is magnetism in the system. Yeah. So there's no moment on the iron side. Yeah.
Okay. So the last question is regarding to the have you are collaborating with people that do the calculation to understand probably the magnetization with pressure? Probably
Yeah.
including temperature is more difficult, but nowadays there are codes that have very well implemented algorithm to work with pressure.
Mhm.
I don't know if you are working or collaborating with computational
Yeah,
scientists.
So
this is that is Monte Carlo, right? Yeah.
So this is our paper on that. So these are our collaborators. Emilio Ortacho is
Okay.
in our lab.
Okay. Yeah.
Yeah.
She's very famous.
Yeah.
Yeah.
And so
Okay.
so this is our paper on that particular
Okay.
thing. So yeah.
Okay. Thank you. Yeah. Okay. Okay. Thank you very much for it.
Sure.
Thank you very much, Sergio Conejero. That was with Emilio Artacho, sir, right? This,
Yeah.
he is in Spain as well. He's sometimes.
Yeah, he's both. But he's like you, Luis. Yeah, he's between or me in many places. Yes.
Well, thank you, Sergio Conejeros. Well, Professor José Fermín, la Universidad de Zulia, University of Zulia.
Gracias, Luis. Thank you, Mr. Siddharth, for your nice talk. And, nice to meet you. No, I have no questions for you, sir. Thank you again.
Thank you. Pleasure to be able to do this. Thank you.
Okay.
Gracias, Luis.
Okay, Professor José Fermín. Well, let's see if the public of Colombia has any question. Ximena, there is any question from the University of Colombia or the public University of Colombia? Ximena.
Good morning, Professor Luis and Professor Saxena. No, we don't have questions from our university. They only say thank you for your wonderful talk. And thank you for this because I learned a lot about this topic. Thank you, Professor Saxena.
Thank you.
Montu, by the way, you know Ximena Velázquez. One time we came across during the in the Cavendish lab. She visited last year.
Okay. Yeah. Now you say it. I remember. Yeah.
Yeah, because we were looking for an furnace.
Furnace.
A furnace with Ximena. By the way, Ximena is one of the is organizers as well of the next version of the conference in Colombia. We don't know exactly when will be in 2025 or 2026. Remember, and in this part of the world, in the Latin American countries, it's difficult to find the funding. And
yeah, I know.
Especially for those people who are governing the funding, administration the funding makes the people who doesn't know anything about science, nothing about science, and they do all the regulation for the scientific.
Yeah, unfortunately.
Anyway, yeah. Okay. Well.
Okay.
Thank you very much, Montu.
Thank you.
Maybe you will say goodbye greetings to the
yes.
Latin American public.
Sure. Very delighted to be able to do this, and thank you, Luis, for suggesting. And it's great to meet our old friends, and of course to meet new people. And I hope that we all continue to fight the good cause of physics, despite all the challenges that are there in our countries. And as I said, I'm open to any suggestions for collaboration, and both experimental and theory or computational. There's always more to do, I have only survived by collaboration. So I really want to do that, and I will say again that I'm still waiting for a way to find a Latin American student to work with. I have had all collaborators and colleagues and even postdocs, but never a student. Maybe I don't need one. They're too good for me.
I think it's because of funding.
Yeah.
Anyway, well,
thank you.
Please, thank you very much, Montu.
Well, thanks, Montu. Nice to meet you again. Nice to talk to you one more time.
Thank you. Yes, same
Please,
here.
Open your camera and your microphone, everybody, to say goodbye to Montu, please.
Thank you. Thank you so much.
Mister.
Thank you.
Nice to meet you.
Thank you.
Margo, gracias. Luis.
Chao.
Hasta luego a todos.
Ciao, ciao.
Ana,
Bye bye. Ciao, ciao.
Okay.